Okay, so this is part 4 of chapter 5. So we're going to be talking about the functions of carbohydrates in the body, and as we've already alluded to, carbohydrates are going to be a primary energy source for our cells. And so the digestible carbohydrates that we ingest, so this includes starch, right, not fiber, these are going to be broken down into glucose or broken down into sugars that are then converted to glucose. And glucose is going to provide energy to our cells, again, 4 calories per gram. Critical energy source for specific cells in our body, especially the brain. It's also going to be a fuel for red blood cells, muscle cells, and again, all of the other cells in our body. There are some cells in our body that can also use alternate fuel sources, but again, glucose is going to be the preferred source. Taking in carbohydrates in the recommended amounts daily is important. Insufficient carbohydrate intake is going to cause the body to find alternate sources for glucose. So if you're not ingesting digestible carbohydrates and your stores of digestible carbohydrates get depleted, your body's going to turn to other sources. One of those is proteins. And so proteins can be broken down and used for a process called gluconeogenesis. This is when non-carbohydrate sources are used to produce new glucose. Okay, so proteins can be broken down and converted into glucose when stores get low. This is going to reduce the amount of protein available for your cells to do things like grow and repair. And amino acids reserves will be depleted and your cells won't be able to make proteins. This will also cause the breakdown of proteins found in other organs, like your muscles and your heart. Okay, and so, limiting carbohydrate intake, in individuals, we'll talk about this in just a little bit, but sometimes people will follow a low-carb diet, and yes, that will end up in weight loss, but some of that weight is going to be the loss of muscle mass. Okay, so we got to keep that in mind. Okay, so when carbohydrate intake is low, what's going to happen is your blood glucose levels, right, so the sugar circulating in your blood is going to be low, and therefore the release of the hormone insulin will also be low. Okay, and when that's low, that's going to stimulate the release of a large amount of fatty acids from your fat storage cells, so your adipose tissue, to provide energy. So again, your body is going to an alternate fuel source. Those fatty acids that get released from adipose tissue, from fat tissue, are going to travel to the liver, and they will be broken down into what are called ketone bodies or keto acids. That can lead to ketosis or ketoacidosis. And those are going to be things that we talk about when we get to chapter 9. Okay. The brain, as well as other parts of your central nervous system, they don't usually utilize energy from fats. And again, there are some cells in your body, like muscle cells, that can do that, but the brain and central nervous system don't normally do that. They can adapt to the use of ketones, these fatty acid products, when carbohydrate intake is inadequate. This will happen during starvation, during fasting. Okay, and again, that's going to prevent gluconeogenesis, and it will try to preserve proteins. Okay, so there's another way that your body tries to prevent the breakdown of muscle. In individuals who have diabetes, and again, we're going to talk about type 1 and type 2 diabetes towards the end of the chapter, but individuals who have untreated diabetes, and so, there are individuals that don't know, they haven't been diagnosed yet with diabetes. They can, if it goes untreated, that can result in excessive ketone production. This type of ketosis is not the result of low carbohydrate intake. So these individuals might be getting sufficient carbohydrate intake. This is instead a result of low insulin production. So a problem with the pancreas actually producing insulin, or it can be because of insulin resistance. The cells that should respond to insulins and take up glucose are not responding. Okay, so again, that's the case with diabetes. So therefore, glucose doesn't enter cells, and so your cells don't get glucose, so they need an alternate source of energy. They're going to rely on ketone bodies from the breakdown of fats for energy. When this happens, there is an accumulation of ketones in the blood because that's going to be needed for your cells, and that's going to create a more acidic environment in your blood. Your blood pH is normally around 7, which is a neutral pH. These ketones are going to cause blood pH to become more acidic, so to drop. That can lead to what's called diabetic ketoacidosis. It's a very serious, very complicated condition, again, in individuals who are either undiagnosed or don't have good control over their diabetes. Okay. Want to mention again, low-carb diets like keto, Atkins, South Beach, or diets that promote long fasting. They're going to promote ketosis. They promote the breakdown of fats for energy. That is a beneficial state for weight loss. Okay, that is a positive impact of these diets. Ketosis can also suppress appetite, which results in a lower caloric intake, and therefore, again, it results in weight loss. It can also increase water loss. So again, that's going to show up in weight, so it's lower body weight. However, over time, or if you are in ketosis long term, that can lead to really serious complications. It can lead to dehydration. Again, it can lead to the loss of lean body mass because of the loss of proteins as well. It can lead to electrolyte imbalances, and in severe cases, it can lead to coma and death. Again, we're going to come back to ketosis in chapter 9. Okay, I just wanted to introduce that here. So again, it can be kind of brought on by either a low carbohydrate diet or also individuals who have diabetes can also see this occur. Okay, we've talked about carbohydrate digestion, but we're going to do it again here. Okay, and so I think it was chapter 4. We talked about digestion of all macronutrients. We're going to specifically talk about carbohydrates here. And so obviously we need to break down carbohydrates, right, starches, disaccharides, into monosaccharides so that they're small enough to be absorbed by our body cells. This process starts outside of our body by prepping and cooking food. And then inside of our mouth, which is not mentioned here. Oh, yeah, so enzymatic digestion happens in our mouth, but also remember that mechanical digestion also starts in the mouth, right? So your teeth are going to be chewing food up into smaller pieces. That's a form of digestion. Also inside of our mouth, we produce what's called salivary amylase in our saliva. That is the enzyme that begins to digest carbohydrates. So carbohydrate digestion starts in the mouth. Salivary amylase will break down polysaccharides, starch, into smaller polysaccharides and into disaccharides. That food, remember the bolus, then is swallowed. It travels through the esophagus into the stomach. Now in the stomach, the hydrochloric acid that's produced in the stomach is going to inactivate the salivary amylase. So there's actually no digestion of carbohydrates in the stomach. That food, which is going to be chyme at that point, will then enter into the small intestines. And again, most digestion in general, including for carbohydrates, is going to happen in the small intestines. And again, this is going to be chemical digestion, although there is that segmentation, right, which is a form of mechanical digestion and mixing as well. So inside of the small intestine, the pancreas will secrete pancreatic amylase, and that's going to enter into the small intestine. That pancreatic amylase is going to break carbohydrates down into smaller poly and disaccharides. So again, we're further breaking these large molecules down. There are additional enzymes produced in the small intestine, specifically by those brush border cells. Again, if you think back to the last chapter, and those enzymes will digest disaccharides into monosaccharides. So here's a couple of new enzymes that we didn't mention in chapter 4. We're just getting a little bit more specific here. Some of these enzymes are enzymes like maltase, sucrase, and lactase. And we introduced you to maltose, sucrose, and lactose, right? Those 3 disaccharides. Here are the enzymes that break them down. Okay, so again, this is happening in the small intestines. One thing I want to mention here before we move on is there are individuals who are lactose intolerant. So lactose is the sugar, the disaccharide sugar that's found in milk and other dairy products. Individuals who are lactose intolerant, they don't have, or they have limited availability, limited functioning of lactase. That's the enzyme that breaks it down. Because of that, those individuals cannot digest lactose in the small intestine, and therefore those that disaccharide ends up in the large intestine, and bacteria there will break it down, which can lead to bloating from gas and things like that, stomach ache, those kinds of things. Some people can have this enzyme persist throughout their lifetime. That's called lactase persistence. So there are individuals that can have dairy their whole life without a problem because their lactose levels don't drop. And then there are some individuals who, after, infancy and, maybe even into adolescence a little bit, it just starts to decrease over time. And so those would be individuals that would end up lactose intolerant. And then there's some people that are just born lactose intolerant. That's genetic. Okay, so there's a genetic component there to whether or not you produce this enzyme and whether or not that enzyme gets produced throughout your life. Okay, so these monosaccharides, so when we break down maltose, sucrose, and lactose, we end up with monosaccharides, the simple sugars. These can then be absorbed into the cells lining the small intestine. They then make their way to the liver, and then they enter the bloodstream from there. Okay. Any indigestible carbohydrates, again, fiber, they're not digested and they end up going to the large intestine, which we've talked about, but we'll mention again in a couple of slides. So here is the digestive system again. We're going to start in the mouth with salivary amylase. That food's going to end up in the stomach. Nothing really happens here as far as carbohydrates. Inside, the pancreas will produce pancreatic amylase. That gets secreted into the small intestine. So we've got further digestion happening in here. Monosaccharides travel to the liver. Okay, anything that doesn't get digested goes to the large intestine. And again, we're going to talk about that on the next slide. Okay, briefly want to just touch back on absorption. Again, we talked about this back in chapter 4, but absorption happens in the small intestine when we're talking about monosaccharides, right? Carbohydrates here. Monosaccharides will be absorbed usually via active transport, except for fructose. Fructose, it's by facilitated diffusion, so it's a little bit different. In any case, this is the lumen of the small intestine, so the opening of the small intestine. And these molecules here are glucose. Right here are the cells lining the small intestines. And so glucose is going to come in. This is the glucose-sodium cotransporter. It is active transport. It's actually secondary active transport, not to get too specific here. And then once here, they're going to travel through the cell and travel out the other side of it and end up in a blood capillary, which again is going to bring these sugars to the liver. And in the liver, here we go. In the liver, all monosaccharides will be converted to glucose. So that fructose, lactose, or any other, lactose, fructose, those are the ones we talked about, maltose, those are going to be converted to glucose. Okay, so glucose is going to be the circulating blood sugar that the liver will then release. Any excess glucose that we end up with, will be converted to glycogen and stored either in the liver or in muscle cells. Okay, and then if blood glucose levels decrease, that glycogen will then be broken down. Okay, really quickly back to the large intestine. So again, we don't have enzymes anywhere in our digestive tract to break down fiber because the bonds between the glucose molecules there are those beta bonds that we just don't have enzymes to break them down. So undigestible fiber travels through our digestive tract and ends up in our large intestine. Okay, in our large intestine, most of that fiber remains undigested and gets eliminated with fecal material. But again, there are bacteria as part of our microbiota in our colon, in our large intestine, which will break down some of that fiber. Okay, not all of it. Most of it gets eliminated with feces. Okay, that is it for part 5.